All right, welcome to the class today. Let's again look at our syllabus to get a feel for where we are. We covered most of these topics. We did support vector machines last time. We did a swap of this particular chapter before, so we covered model tuning and what underfitting, optimal fitting, overfitting means. As you see, we got a couple other techniques that are very popular. Just like SVM, we have random forests and neural networks coming up. And then this is a very important topic as well, week 7, which talks about how to quantify and evaluate your techniques. So this has nothing to do with the internals of how the technique works. This is more about given any technique and given any report from a technique, how do you evaluate a technique? What are the popular metrics? So this is very useful even from a business setting, because a lot of people that are, say, just MBAs and not really technical from a machine learning standpoint, or your managers or your coworkers and colleagues these days are getting more and more educated in this terminology. So in big companies, they do understand what these metrics are, although they do not understand very well how the techniques work. So this is becoming more and more of a business terminology as well, apart from being just a technical way to quantify how your classification model is performing or how your regression model is performing. For regression, the evaluation is a lot easier because all you need to look at is the mean square error, right? So how far away is your prediction from the true ground truth? And you always have cross-validation, so you can compute cross-validated error for mean square error. Now for classification, it's a little more complicated. It's not one number. There's a lot of trade-offs of different metrics that come into play. And you can compute those metrics under the cross-validation setting as well. So what we'd be doing now is, since we covered these 4 topics, before we jump to new techniques, since we covered one popular technique already, we'll be covering these topics of how to evaluate your techniques. That way you will have an end-to-end understanding of how to pre-process your data, how to handle categorical data, one particular technique that you at least understand what those parameters are. SVM has 2 parameters that you need to tune using cross-validation. So you covered all these concepts in some context for SVM. So this will bring the last phase of it, how do you evaluate your SVM into play. So after that, we can cover random forests and neural networks, and everything else stays the same. For random forests as well, you'd have some parameters that you can tune using cross-validation, and then you would use these metrics to evaluate it. So that will be like one end-to-end pipeline that can become your first project for your resume as well. So before we get into that, I have a question. Have any of you already identified any data sets on the UCI repository that caught your eye that you might want to work on? Anything you can share right now on what data sets you might have identified? If not, you can email me. Do you have any preference? Let's see. Chun, there's Chun first here.
Oh, I haven't looked it up.
Okay. So sure, yeah. So I would recommend you guys to just browse the UCI machine learning repository and find some data sets that you can do your project on that using some of these techniques. And that would go into your resume, because whatever you're doing, if it does not end up in your resume, it is then just for your intellectual learning, and it will not really add anything new to your resume. So
yeah, understood.
Yeah, cool. Raghu, do you have anything?
Not identified anything yet.
Sure, you can email. This is a very simple conversation. We can just do it on the email. Okay. I'm just asking everyone this because we started with Jim. So Sashi there.
Hey, Brennan. Actually, I mean, like from masters, I always have one data set in my mind. That is like to predict the player's price in the IPL. So I was not sure how to do that.
To predict the player's
price in auction.
Oh, in the auction.
I tried doing that during my masters, but ended up.
So this is an auction of products or like teams or?
Yeah, teams.
Oh, IPL. Okay, yeah. So teams.
Yeah, you have set of players in the auction, so you just need to predict how much price they might go in the auction based upon their performance in the previous matches.
Yeah, and then you also know how much they were auctioned for in the previous matches.
Yeah, we do have those data.
Okay, yeah. So then that might fit into this. If you can share in whatever form, the Excel sheet or whatever you have, the data, and even the head of the data, you don't have to share the entire data by email. Then I can confirm.
Yeah, sure.
Also in these settings, and then also put in a sentence about what is the size of the data set.
Yeah, that's my question actually. Means how much stats we have to take, means like what all years we have to take.
Right. So this is very generic, like, you don't want to do another scientific experiment. Although,
Excuse me.
Yeah.
sample size, just for talking sake of talking about it. If you have like 100 records or something, it might be too little, basically.
Okay.
So, if you have like 1,000 records or more, 1,000 rows or more, your variables will differ, obviously.
Yeah.
How many you have. You should be okay. You should be okay with running SVM and all these techniques.
Okay.
If you have, again, like big data, right? If you have millions of records, then you might have trouble just handling this data because of the size. Then, because you're not using any big data technologies like Spark or whatever here. So then you might have some issue running SVM or whatever these techniques are. So for project purposes, I would recommend not the big data for your first data set, because then you would get confused between learning how to handle big data and how to do data science. You will be doing anything properly. So maybe something that's reasonable, like 3,000 records, 55.
Yeah.
Or even like 1,000 records, okay. 750 is okay. Like 100 records or below, like 200, maybe too little. Generally saying.
Yeah.
Yeah, so you can send me some data, the head of the data and some detail on the size that you have. And if anything else that catches your eye, like if it has any incomplete entries,
if not that, I want to do on some financial data actually.
Yeah, so that is another
banking
set.
data.
Yeah, so financial, again, two things. Some data set would be time series data. Then it doesn't literally fit into SVM straightforward, although you can run it. Because time series analysis is a separate set of techniques.
Okay.
So something like stock market. It's like sequential data. Based on what has happened in the past sequences, what is the next sequence? Slightly different from machine learning problems. But there would be banking financial data sets where your rows, your primary key or your rows are not really time series. It's not time index. Maybe like, is this customer based on his past other variables? Is he likely to be a defaulter if I give him a loan, or will he pay back my loan?
Yeah.
So, you can use his T-cost over other things and then determine if he's a risky customer for the bank. These are all standard machine learning problems. So yeah, okay, yeah. So you can send me something, and if you find any issue, you can always find on UCI as well. So you don't have to find on UCI everybody, right? You can find whatever catches your eye. UCI is there if you want to find something. So Venkat, any data set that caught your eye by chance?
Yeah, actually I went through the links, but honestly I did not download anything. Even in past I downloaded some from Kaggle also, kaggle.com.
Okay.
So not really concreted anything like, okay, what exactly the use case, but I'll figure it out through this week.
Sure, yeah. Yeah, I think you don't have to, Kaggle maybe you might want to download, but UCI, usually if you just read the top, there is a table of characteristics of the data and some stuff you give in description that should give more than enough information. It is usually a link called data folder. If you go to any page on UCI, when you go to any data set, there is a data folder or description page. You can just read over it. Then if something catches your eye, then you can download and just see.
Okay.
Otherwise, it will give you all the information there, what variables, what is the context and story. Okay, so yeah, it would be great if you guys can email me, because this is something we definitely want to hold it by its tail and finish it as a project and add to your resume or learning. So yeah. Okay, so let me share my screen. Okay, looks like I didn't share my screen when I was showing my syllabus, but all I was saying was we covered these topics, including SVM. We covered this as well. We discussed about model tuning and cross-validation prior to SVM. We'd be skipping these two for now. We'd cover them again next week. but we'll be covering this topic. This is what I meant in terms of how to evaluate a classification technique. Then you can do any technique end to end because you know how to evaluate it as well. Okay, so this time we'll be using an external slide. I'll be sharing these links with you. Usually we use our own slides, but this should be from outside. But sometimes our own slides are also a mix of what's outside. These are standard topics. Okay, so yeah, you're talking about evaluating machine learning methods. Yeah, something more relevant would be evaluating classification methods in machine learning, not regression. Regression is a lot easier. So SVM, for example. So structure of it. As you see, these parts, we've covered it before in terms of what train test set is, what cross-validation means. So we'll be jumping these topics quicker. These from here onwards, from confusion matrices, we have some, these four would be more solid topics, at least these three. Because, as I said, for classification, it's not about one metric. There is so many metrics, so you need to understand the trade-offs of how your method is performed. Okay. These are some more metrics. Like I said, there are so many metrics in classification. So these are the TP, FP, T, and FN stand for, the content stand for these. True positive rate, so on and so. We will cover these as we go down. So this is just to give you a, okay, just to give you a heads up of the background. You know this stuff already. We have a notion of, we are talking about only data sets where everything is labeled. So it's a supervised learning setting, and then we're talking of setup where we have training and test set. What we usually do is we apply our method on the training data. We learn our method on the training data, and then you have a learned model, and then you apply it on the test set, and then you get some estimate of accuracy. Now we will zoom in further and refine this a little more, but this is the overall setup we are in. So this would be your SVM, for example. And when you figure out what are the exact parameters of SVM you need to use, then you have the learned model. Because without the parameters, you don't know what is your exact learned model. So in SVM, the parameters are cost and gamma, which we discussed yesterday from the last week. It is a more mathematical discussion. So now there comes a point of concept of well, learning curve is a very generic term, but the concept here is people can ask questions about different aspects of your learning method. So one aspect could be, how does the accuracy of your technique change as a function of the training set size, right? So if I use a small training set versus a larger training set. So here the answer is a lot more straightforward for all techniques. The amount of improvement is different, but usually the greater the data set size, more the improvement. So for example, here, on some specific data set, logistic regression, once you have above 1,000 records, the improvement is not much on the training set for that particular data set. For decision trees, so it's like random forest kind of techniques. More the data, more the better. Your accuracy keeps increasing, right? So yeah. But this is a much simpler question and simpler answer. What is more difficult is performance of the method, not just in terms of accuracy, but other metrics as well. Because accuracy is just one metric that that is useful, but there are other different dimensions and different metrics, different angles you can look at the performance of your technique from. And then even in terms of estimating any curve, there is there is improvements that you could do in estimating that particular curve. This curve, if you see, each point has an error bar in here. So he's not sure. He only knows that at this amount of sample size, say this is 750, for example, if you use 750 records of training data, then he estimates that the accuracy is somewhere between 0.77 and 0.81 or 8.81 or something like that. So he's not sure about one number. So this is the error bar. Here it is much sure. He's very sure if you have 10,000 records, it's definitely 84%, a little less than 84% accuracy. But say if you had only 50 records, he has no clue if your method is performing at 0.70% accuracy or close to 80% accuracy, 79% accuracy, or 785% accuracy, right? So there's a big error bar. So as you see, as your data set size increases, the error bar is becoming smaller and smaller. You're becoming more confident about your estimate of accuracy. And you can do other things as well to improve your estimate of accuracy. We would cover these things in a separate topic, but the overall idea here in a one slide setup is, if I were to put it in one slide, it is you can basically you can repeat your experiment many times. So each time you choose a different training set in a random of a size S, but you randomly choose. So every time you pick S records as a training set, you get slightly different training set, right? Slightly or maybe very different training set. So you're doing this on these computations of what is the accuracy given a given size of a training set. You do it multiple times. You average your standard deviation and error bar around the average. You can use that not only for accuracy estimation, for other estimations as well. It's always good to resample, and instead of doing on one training set, you can try multiple times. So this was our previous slide in terms of our setup right here. We are zooming in a little more into this part, which you already studied in the tuning part. So basically in your training set, so you have a training set and a test set. Test set is completely aside. Your training set again gets divided based on cross-validation into multiple training and validation sets. And then you learn models, which means you tune the best parameter. Then you try multiple parameters, you choose the parameter that gave you the best model. So that is the model you're selecting. So that will be your learned model. So this is zoomed up version of even more detail. So for SVM, you choose the best cost and gamma, right? That will be your learned model. So this is the same thing we were discussing 2 slides back. Instead of using one train test partition, you can try different train test combinations, which will give you even better estimations. So like this, different kinds of training and test sets. You randomly partition from your original data. Each time you see how your performance is, and then you average it. And there is a notion of stratified sampling. These days, when you do sampling, cross-validation in R or in Python, there is an option where you can literally mention cross-validation with stratified sampling. So this is literally like an option. You in your function call, you use this, and then you say equal to true or like equal to 1. And basically what this does is, it's also good to understand what it's doing, right? So that you can use it when required and not use it when not required. So what it does is, if you have a data set that is unbalanced, in your original data set, if you have, this is not that unbalanced, but you might sometimes have even extreme cases where, say, plus and minus are 2 kinds of records, 2 classes, and if you have a lot of pluses, all these are pluses, or all these are pluses, and only few minuses, like maybe 80% of your data is pluses and 20% minuses. Class 2. So you have one class being majority, one class being minority. So if you have an unbalanced data set, then stratified sampling tries to sample in a partial way so that it will sample more from the unbalanced part, resample more from this part and from the minority, and then less from this part, so that in your training and test set you will have a little more balance in terms of the 2 classes. And then you apply the same, all your techniques and all that, this part. So stratified sampling helps. It's an option. If you read it somewhere in any function call before you apply a data set, then you know that you should be using it if you have, or it's one of your options to use if you have an unbalanced data set. And that's what he writes. So based on some proportion that you want to match, right? If you want to have 45-55 kind of a balance instead of 80-20, then based on that proportion, it will sample more from each class individually. So it will sample more from this set and then lesser from this set. So that I think overall your proportions match up to what you want. This is cross-validation, which also happens in this stage in here. How do you learn models and select model? We do in this arrow, right? These 2 arrows. This part is selected by, is done by cross-validation, right? We studied this in one lecture as well. So so this is k-fold cross-validation. You divide your data set. So each time you drop 1 fold, so these are different subsets you divide your data into. So say first time you drop this fold, you train on these and you test on this. That's what he wrote. You train on S2 to S5, you test on S1. Next time you drop this guy, you train on S1, S3, S4, S5, and you test on S2, so on and so forth. Each time you test, you have an error here, or your accuracy measure. You can average all your 5 measures to get your cross-validation accuracy. That is cross-validation. So here he wrote, 11 by 20 were correctly predicted in this set. 17 by 20 were predicted well, so and so. So your average accuracy is this. So this is just literally like your examinations, You have 5 midterm exams, you have 5, performances of your, how many marks or score you got, your grade, and you average your score. You get your final score, that kind of thing. That's simple as that. Then in cross-validation, many kinds of cross-validations are there. One is k-fold cross-validation. You can choose 10-fold, 5-fold. You can also do leave one out. What is leave one out? Which means if you have n rows in your data set, instead of dividing like this, each time you leave only one row out. So if you have like 1,000,000 rows, or like 1,000 rows, you leave one row out. You train on all the rest of the rows. You test on the row that you left. The next time you leave this row out, but you train on this row and everything else. So you test. So basically your number of folds are only 2, and the size of your test set is only 1 record basically. So you try every time you leave one particular record, you train on the rest and test on that. You average your errors. That will leave one out cross-validation. Stratified, here it is used in unbalanced situations when your classes are unbalanced, so and so. And literally in your Python and our function calls, you have these options of what kind of cross-validation you want to do when you do a function call. So it's good to understand what it is, what's happening internally. So we've studied this, what happens internally in terms of cross-validation. We do the train and test. So this is just the pseudocode for what k-fold cross-validation is and how it can be used to choose a particular parameter in a given technique. So there's a technique we've not studied. It's called k-nearest neighbors. Just like SVM has cost and gamma, you need to tune correctly for your technique to work well. Here you need to choose the choice of k, how many neighbors you want to use. So for different kinds of k considered, you compute cross-validation error and you choose the k that gives you the best cross-validation error. That's what it is. All right, so that gives you some background. Now comes the true context to what we wanted to cover, which is this. We wanted to cover these different metrics. Okay, so we start with confusion matrices. It's an important metric. So you might have a 2-class classification problem. You might have, let's see, 1, 2, 3. You have 10-class classification. So here basically, say you had a model that is, say, being used by a video camera, like a computer vision setting. Maybe someone is monitoring everyone in the room, and it is trying to classify whether the people are bending, what activity they are doing. Are they walking, skipping, running, etc. And the camera needs to have some intelligence to be automatically able to classify, because it's not the human eye, it's not a human brain. So you need to have a model that you load into you do computer vision on based on data coming from the camera. Another option could be, say, you had a smartwatch. Basically, the smartwatch dataset is available in UCI as well. So all the Fitbits and smartwatches, they have a lot of sensors like accelerometers, gyroscopes. All these sensors have, information of how quickly you're moving, how your elevation from the ground is changing. Are you bending or going up? How the pressure is varying, because these have very sensitive pressure sensors in your smartphones as well. Your phone literally knows if you're at a height of 4 feet, or if you're bent at a height of 1 feet, or at a height of 7 feet, or height of 50 feet, where are you elevated, and it can precisely measure that. It can also measure the angle. That is how, when you tilt your phone, automatically your screen starts, moving in a way so that it is still straight. It knows how to adjust its screen. It doesn't, when you tilt the phone, its screen doesn't turn around. It turns back in a way so that you can still read it. You don't have to turn your neck to read it. All this is happening because of these smart sensors in your smartphone. In a way, your smartphone is an Internet of Things device. It's an IoT device as well because of these sensors. But each sensor only collects some specific feature variable, right? It collects pressure, temperature, elevation, rate of your velocity at which you're moving, your acceleration, etc. So the angles are measured by gyroscopes, your acceleration by movement, velocities by accelerometers, etc. So based on all these input feature variables in a supervised learning setting, how will your phone be able to know, or your smartwatch be able to know whether you're bending, jumping, whatever, you're skipping, etc. Or you're waving at someone in one way, or you're waving in another way, maybe there are 2 different kinds of waving, How does it automatically know? So the point is activity recognition, either from video or from smartwatches, etc. So say in that context, This is a true classification problem. You have 10 classes. You don't have 2 classes like in email where you had only spam or no spam. Then there's a 2 by 2 matrix. If you have 10 classes, the confusion matrix, what we're discussing is a confusion matrix. It's a 10 by 10 matrix. So this literally has a lot of useful numbers. So if your model predicts all the 100 bends as 100, then it's a high accuracy. If it predicts when you're running only 89 times correctly and makes 11 mistakes, then your accuracy is 89%. So here it is giving you not overall accuracy, but it's giving you accuracy based on each class that you're trying to predict. So it's a class by class accuracy. If you want the overall accuracy, you can sum up all the truths and divide by the total number of predictions. So there is a pattern that you're seeing here, which is the diagonal values, because bend being predicted as bend or skip being predicted as skip. This is skip here, this is skip here. Yeah. So how many skips were predicted as skip? 100 by 100. So very good. Waving, 67 was predicted correctly, but 33 was predicted as another kind of a wave because he was measuring 2 waving at somebody. So there is confusion wave 1. Jumping as well. 89 times they predicted it as jumping out of 100, but 11 times jump was, the model thought jumping was instead skipping because, they're kind of similar. It's not like running and jumping are very different, but jumping and skipping are kind of different. It's like hopping, right? You're going up in the air, so that's what your smartwatch is saying. Elevation is increasing, so on forth. And usually if you're not like an Olympic jumper or like a high jumper in Olympics or something, you would usually jump as much as you would in skip. It'd be very similar amount of height. So I can imagine your height, pressure, everything's changing. But there is always some variation that will, in terms of how your body is moving to distinguish jumping from skipping. So yeah, I can see some uncertainty in the model there that they used. They might have used an SVM, you never know. So this is a confusion matrix. We want to study different metrics, right? So it's a confusion matrix. So if you see there is a pattern, the greater the number you have on the diagonal entries of the confusion matrix, the better is your performance. Lesser numbers on the off diagonal, lesser the errors. That's what it's a nice way to look at it quickly. So you can always have a heat map or color coding as well if you want human eye to figure it out very quickly if you have many class problems. Also, there is a notion of training confusion matrix and cross-validation confusion matrix. So training error is, if this is your training thing, then I would not be very particular about looking into it because training error doesn't really matter as much as cross-validation error does when picking how good a model is. So if this is your cross-validation error, then this is a good thing. It's doing reasonably well. It's performing reasonably well. Except for waving, it's making a lot of mistakes between wave 1 and wave 2. At least it's not saying wave 1 is equivalent to running. Waving and running are very different human actions. So in an email setting, say if you had only 2 class problems, then you have a 2 by 2 confusion matrix. So again, your diagonals will be the ones which are the good entries. Off diagonals are the mistakes. So you have a positive class, negative class, or spam class, email spam, non-spam, no spam class. So these are your predicted classes, your actual classes. So how many spam were predicted as spam, right? How many positive class was positive? So higher it is, the better. How many positives were predicted or classified falsely as negative? So it's a false positive. Sorry, this is the actual class. Sorry about that. How many actual positives were predicted as positive? So the more the better. How many actual negative were falsely predicted as positive? So this is the false positive. The diagonal should be off diagonal. Similarly, how many actually positive class or how many actually spam class is negative? So it's a false negative. So it's not a true negative. It's falsely predicted as a negative. So how many actual negatives were predicted as true negatives? Same pattern. So the 10 by 10 class confusion matrix is a 2 by 2 confusion matrix. So how do you compute the accuracy for all your classes together, right? These are individual accuracies. So what do you get accuracy for the entire method? Then all you have to do is obviously sum up the diagonal entries and divide by all numbers. Because if you sum all the numbers, you get the number of rows you have in your data set anyway. This is your total size of your data set. This is how many correct predictions you made, how many correct classifications you made. Same thing here. You sum up all the diagonal entries and then you divide by all the entries in this matrix. The sum of all the entries in this matrix. Right, so that is known as the accuracy metric, which we know about. And then we know about confusion matrix, but is that the only metric that you care about? No, that is the point of this class. There are so many other things that come into play when you're working with a classification problem. So there are some reasons why accuracy is a great metric, but it's not good enough. There are other things you need to consider together, right? So, for example, another example I wanted to give here is these this terminology of true positive, false positive is very common even in the medical field, in a clinical setting, medical field, right? Because you have medical tests that you do, on our blood or whatever, to decide if the person being investigated is a patient or is sick or is affected by some particular illness or not, right? So basically, if you're checking for, I don't know, let's see, cancer or HIV or something, you hear these terms very, very commonly. So it's the same terminology being used here. So if someone who is really positively affected was the method, most of the times who is positively affected is classified as being a positive patient, then it's a correct prediction. Your method is working. But if your method, is making a lot of false positives, that is a lot of havoc, because you're saying there is some very tough to control illness that actually the patient does not have. Actually, he's a negative person. But if you say he's HIV positive, and if your method keeps saying that many, many times, then that's a very bad classification method, right? Because you'd be probably putting him under a lot of pressure, or maybe financial pressure, or maybe a lot of false treatments that he does not require. So this is common notions. Another area where you use these terminologies. So these are all different classification problems that we have models for. So these models are real life techniques and instruments. They're not really machine learning methods, but they're still solving the classification problem, right? Another very common area where this idea comes up is in emergency services and 911 calls and all that kind of thing. If you have a false alarm, right? So let's say in a fire situation, a false alarm means what? It's a false positive. Alarm is a positive, right? Because you're falsely thinking an alarm set off, but truly the truth is there is no fire situation. This kind of terminology comes up there too. So yeah, accuracy is not good enough. Why? Because if I'm doing this number very nicely and if I'm doing this number very badly, then if I look at just this accuracy, it doesn't give me enough. But the other way around, if I do both these numbers, if my method is performing very well on these two numbers but doing very bad on these two numbers, that's another situation that can come up. So if you see, how do you quantify these different situations, right? Because I can always be predicting the positive and negative class correctly, but I can also be making a lot of false situations. So is 98% accuracy good if 97? Yeah. So say, for example, if my data set was highly unbalanced, right? That's the example he's giving. Skewed data. Skewed means I'm imbalanced. Say if I had a data set of 100 rows, 99 rows were spam emails. One row was no spam email. If I automatically predict as spam everything, I'll have 99% accuracy. But if you look at my false positive, I would have one false positive. But I'm not quantifying it, right? I'm saying 100% accuracy, but I'm not talking about the one false positive. Now, it could be a more difficult situation where 80% accuracy I might be having, but my false positives may be even more, maybe more than 20%. How would I know that? Now, there are different misclassification costs. This is another situation, right, where your cost you pay in your society or in real life, in research or your industry for making one kind of a mistake may be a lot more than the other. So maybe getting a positive wrong costs a lot more than getting a negative wrong, right? So, for example, in this situation, if you're talking of HIV, if your method is falsely classifying HIV negative, a person who does not have HIV as having HIV negative, of course you're paying a cost. You're giving him, some panic, right? You're giving him some issue mentally, and customer service issues and all these kind of situations, right? Societal situations. But in the end, you won't be losing him, right, to the issues of the disease, right? The disease in the end, regardless of what your class has said, he will be hale and hearty. But the other way around, if your method is calling a HIV positive person as HIV negative, then you have an issue, because the person is sick and your method is saying you're perfectly fine and you're sending him home, so you're not giving him the treatment that he deserves and he needs. The earlier the better. So the cost you pay here is a lot more. Similarly, in our judicial system, in the court of law, you usually use the notion, you have different costs, right? That's why we use the notion, you're innocent until proven guilty, because the cost of calling an innocent person truly guilty and assuming that beforehand and saying you are guilty until you're proven innocent, the cost that you pay there is a lot more in terms of what the society, the principles the society believes in. So you have a different cost of making one kind of a mistake versus the other. So in that situation, how do you, what are the other metrics that take your false positives and negatives? In fraud detection, the area that I work in, Amazon cares a lot about customer satisfaction in terms of its business principles. It is kind of obsessed about customer satisfaction. So it hates the fact that our models will, the situations where our models will take a truly innocent and genuine customer and call him fraudulent and give him all actions and deterrences, assuming that he's fraudulent, that is something Amazon hates, because that is affecting your customer satisfaction, right? So that is basically a false positive, right? He's innocent, but we're calling his account as fraud, we're blocking his account, we're shutting his account down, we're erasing his account, different kinds of actions. We're reporting him to the police or whatever, right? So you don't want to do that. So in Amazon, we care about having a very low false positive rate while having a high these rate. We're okay with slightly higher false negative, but false positive should be very low, because we're okay with thinking a fraudulent customer is not fraudulent, but we're not okay with calling an innocent customer as fraudulent, right? So there are different trade-offs involved. So there are three different situations we talked about. So how do you truly measure these individual metrics that we talked about? That's where these newer numbers come in. The true positive rate. Everything comes from the classification matrix. The true positive rate is also known as recall. It is basically the true positives by true positives plus false negatives. So this ratio. Because the total number of positives, what is the percentage true and what is the false negative rate, right? Similarly, false positive rate. False positives by true negatives plus false positives. So this number by sum of these numbers. So these are newer, finer details that when you look at all these numbers, you can analyze the performance, because it's not about only accuracy. It's a great metric. It's very useful, but you need to understand how your method is performing across these metrics as well. And there is a concept of ROC curve. These days in Amazon, a lot of people who have no idea about machine learning still can interpret a ROC curve when they sit in a meeting. So this is becoming more and more popular, just for business purposes as well, to be able to understand what an ROC curve of a machine learning method is. So this is basically, if you have different thresholds that you can choose. So say, for example, logistic regression is a classification technique. What it predicts is it does not classify, its output is not class 0 or class 1. It doesn't predict the class itself. It just says probability. It says, I think this particular row has a probability of class 1 at 80% probability. But this particular row, I think we're only 30% probability that it is class 1, 70% more sure that it is class 2. Every time it's predicting a soft number. So the question is, what is your cutoff? Above which it is class 1 and what below that probability it is class 2. How do you know the cutoff? Some people may say maybe 50-50, right? If any class has a more probability than 50%, then it is that class, the majority class, right? But that may or may not be good enough for cross-validation purposes, because as you saw in this diagram that I keep drawing many times, that it's useful in this context again. So as you increase the choice of parameters, you have low complexity and high complexity models, and you have the error here. So your training error keeps on reducing as your complexity increases, but we care about cross-validation error, which at some particular level of complexity becomes the least. And so if you use a model at lower complexity, you're underfitting. You're having more error. If you're using higher complexity, you're overfitting than required, and you're still having more error. But if you use the right level of complexity, then you have the lowest error, right? So you don't know if the 50-50 threshold in logistic regression is good enough, right? So say I predicted something like this, and if I say anything about this value is class 1 and anything below this is class 0, if this is my output of my logistic regression, the probability basically. That is one way to say. But sometimes my prediction may be like this. Logistic regression might have predicted probabilities like this. So then this is not the good cutoff. The exact half value is not the good cutoff, especially this was very long, for example, right? So this is less than half value. This is the half value, the 3% cutoff, but that happens to be here. It is much lower. So if I say any number below this, then it is class 0. Any record with a probability predicted above this value, that is class 1. That's a better separation, right? So, and your choice, you are also allowed to make a few mistakes sometimes, like little away from what you think is correct, because this is maybe the training error picture where maybe cross-validation varies in a different way in terms of your choice of what this threshold is. So this threshold is basically a tuning parameter. In SVM, you can talk about cost and gamma that decide how your cutoff is between one class to another, at what cost and what gamma. So basically, that threshold is deciding what your true positive rate is and what your false positive rate is. Because every time you change your threshold, you have a different model. Your performance in your confusion matrix keeps changing. So what is an ROC curve? By definition, you're just plotting for every threshold, all possible thresholds, you're plotting the true positive rate versus your false positive rate versus the true positive rate. So think about this a little while. It's always good to interpret a plot a little more and understand it before just listening to the definition and leaving it there. False positives, it's a bad thing, right? You want to have low false positives. True positive is the diagonal thing in the confusion. True positives, the better. So what does that mean? Your curve, the higher it is and closer it is to the origin here, and higher it is on this axis, the better it is performing. So basically, it says at this level of false positive rate, I'm performing at this amount of accuracy. But if I allow my business to be able to take more false positives, then I will be making a lot of false positives, but I will be getting greater accuracy. So there's a trade-off. So say in Amazon, we don't want to have very high false positives. So then we have to choose a threshold, not just based on cross-validation, but based on business needs. I would say I would choose a threshold that will have less false positive. I won't tell you how much, but I want to make sure my model always has less false positives, and I will take whatever accuracy it gives me, because I don't want to classify a good customer as bad. I'm okay with misclassifying and thinking a bad customer is good enough. So based on your situation, you can, once you have an ROC plot, you know where you want to operate in. So if you want to operate at this trade-off, then you choose that threshold for your technique. If you want to operate at this trade-off, you choose that threshold. Whatever threshold you choose, you know what your trade-offs are if you go above or below that threshold. So this is the ROC curve. So for SVM as well, you can draw an ROC curve. This is a true example. This is like a cartoon, but this is like from true data on some particular data set, some bioinformatics data set. They use 3 techniques for classification. So as I said, more the TPR that you get for low FPR, the better. So this higher curve is much better performance than these two curves, because it's getting, for very small FPRs, it is getting higher TPR, higher accuracy than the other curves. At this level, once you are above this amount of false positives, then these two techniques are similar performance. But then you can see what these two techniques are. They're basically Bayes-Net and naive Bayes. Naive Bayes, we've studied it in our first lesson or maybe second lesson. Naive Bayes is a very simple technique to tune. You can even do it on paper for small data sets. Bayes-Net is a very complicated technique to tune and train your model. So then you might think, if your business is okay with operating at this false positive rate, and it cares more about high true positives, then you can think, hey, these two techniques are performing same level. This is like a very stupid, very simple technique. Why should I bang my head and use all the big data frameworks to train a Bayes-Net? I'd rather use just a very simple technique. I can tune it in like a second and I can handle millions of records and I still get the same performance. All these kind of business decisions in different ways and contexts can be made once you have the ROC curve. So yeah, this is basically talking about different kinds of curves and what it means at different points on the curve, right? So if you're here, it means you have very high false positives, right? So obviously, the ROC curves at the highest point, when both is 100, they both become a straight line. The curve becomes straight line, because if I make 100% false positives, then obviously I can also make 100% true positives. So basically I'm saying, if someone is asking me to predict, I will explain that a little more. So if someone is asking me it gives me a map of, say, New York City, and asks me to pinpoint where crime will happen using some boxes. Say, I use a method, or I talk to some detective or whatever it is, CIA person or investigator or police officer. And I say I come up with these 4 boxes is where crime will occur tomorrow. If my crime happens outside, in reality tomorrow, then my accuracy is 0. I caught no crime. I just wasted the time of police officers by sending them to these boxes for longer time while they were supposed to roam here. But in this extreme situation, the cartoon situation where you go to the very end, what I'm saying is, I will say this is the map. I will say, instead of putting 4 boxes, I will say this entire map is my box. I'm saying crime will happen somewhere in the agency. That everyone knows. Tomorrow crime will happen somewhere in the agency, obviously. So what is the trade-off here is your true positive rate is high. Your 100% accuracy, it's not useful because your area that you're supposed to patrol is a lot more than your officers have resources to patrol in all the time. Right? So there's another trade-off between resource efficiency and accuracy. Similarly, you have a trade-off between false positives and false negatives, and true positives and false positives, true positives and true negatives. So say again another situation, same story. Say I put a box here, I put a box here, I put a box here, say put another box here in terms of my predictions for tomorrow. And say crime happened here tomorrow, crime did happen here, great. Crime happened here as well, extremely good. Crime happened here as well, good. But did only 4 crimes happen? No, maybe 40 crimes happened. So their crime happened outside as well, all over the place, in different specific spots. Say a lot of crimes happened. So now, if I give you only one number in terms of accuracy of my true positive rate in my boxes, I will say I predicted 100% correctly. There were 4 crimes that did fall in all my 4 boxes. No box was left empty. And I can tell to my police chief, hey, you should pay me $100,000 or $1 million every month or every 6 months because I'm able to predict 100% crime. I have a crystal ball with me. Then if he's a smart police chief, he would ask you how many of the crimes happened outside your box, and then I'll say 100 crimes happened outside. My box has caught 4 crimes out of 4. But my true performance is 4 by 104, which means the amount of crime that I really caught was 4 by 104, which is like 3%. So then he will say, no, this is not good enough. I will not give you my contract, right? So here, these are the true positives, but there is a lot of false positives false negatives that have happened because all these were truly in actual situation they were positives, but your method treated them as a negative. It thought crime would not happen there. So you have a very high false negative rate and also a high true positive rate. So this is a situation where your true positive is high. It is catching wherever your boxes are there, it's catching crime. But where your boxes are not there, it is missing a lot of crime. So this is very high as well. So that is why the recall rate is a great metric. It is measuring the proportion of true positive by true positive plus false negative. So this will give me a lot useful number, right? So that's the reason we don't care about just accuracy. We care about a lot of other metrics. So that is the ROC curve. This is, again, pseudocode for creating ROC curve. You choose different thresholds. For each threshold, you compute TPR and FPR. You output that as a plot, basically. So similarly, like recall, which you studied, there is precision. This also matters a lot. True positive by true positive plus false positive. Then you can also have a curve between precision and recall, which is popular. So this is basically, again, these two metrics you compute, you plot them at different thresholds that you're choosing for your method. And based on whatever trade-off your business needs, you would choose a trade-off. Because there is a trade-off. You cannot get 100% precision and 100% recall. There is a trade-off. So there's another ROC curve, mammography. So this is like for, say, breast cancer detection, right? So how many times you're really detecting the cancer and how many times you're not detecting it, etc. For different methods. This is the precision recall curve for the breast cancer detection. And then now you can have these curves, be it the ROC or the precision recall curve for your training data set, but we don't care about the training data as much as we do about the cross-validation. We care about both together, but more we care about cross-validation. So how do you do it for cross-validation? It's simple. There are different ways to do it. One is you have different test sets, right? When you divide your data set into cross-validation data sets, you basically predict the curve, you plot the curve in terms of performance of each test set. So what do I mean by that? So this was your, these were your folds, right? So when you predict on, when you leave S1 aside, train on these and predict on S1, you get some error, right? So which is your accuracy is the error, but you can get precision, recall, TPR, FPR, TP and FP and everything for just this prediction in terms of what is your TPR when you predicted on S1, then what is your FPR? You can compute the entire confusion matrix. So you can basically have an ROC curve here. You can have another ROC curve in this situation. You have 5 ROC curves. When you draw the 5 ROC curves, and then what you do is you basically have this stuff. So let's go there again. So you draw individual ROC curve, each curve as a function, but plot the average curve. So that is one way you get a cross-validation ROC curve. Right. So the topic about confidence intervals on error, this is talking about error bands, because what you think is the error may not be the exact error. Maybe it is there is some error band. Maybe the error is not exactly 75%. Maybe the error is 75 plus or minus 7%, right? Maybe it is between some number to some number. Like how do you get these error bands on what you're estimating in terms of what error is, etc. But this is a separate topic, as you would see we would cover in week 9 here. We're week 10, so we're covering week 9 and 10, we're covering confidence intervals and all this. Once you have the understanding of these topics, then you will understand this part of the evaluation. So this is something that will come into the next lesson. So yeah, we are about 2-3 minutes overboard. Any questions at this point? Concerns, comments? But otherwise, yeah, we covered what we were supposed to cover in this lesson.
So in general, I'm getting a call.
What you said seemed very choppy. I was not able to listen. I'm not sure if the rest of you heard it. Can you say that again, Venkat?
In general, you are what kind of models do you usually do?
Oh, we do use random forests, sometimes SVM, but we do use random forests a lot. Neural networks is all the deep learning thing, so we use the deep learning once in a while in many places, in Amazon as well. But random forest is very popular. Basically, we have implementations of random forests that really scale to very large, big data sets. That's one reason. But we're moving to other techniques as well. But within our syllabus, random forests in general is one that we use very popularly. Yeah. Any other questions?
I actually have a question.
Sure.
So this was like in one of my interview, the interviewer has asked this. So it was a financial credit card company. So like they were giving the finance money to the customers.
Mm-hmm.
Like there's a customer who doesn't have any previous SSN history or so. So how do you find the acceptance rate of that particular customer?
So do you have some variables about him and many other variables you don't know about him, or all you know is his name?
All you know is his name, that's it. That's what the interviewer has said.
Yeah. So, I mean, that really happens, right? Some might be a customer, maybe some customer from India or China, and I have no record in America about his credit history or his people score. Doesn't have a credit card.
So how do you find the acceptance rate of that?
Sure. So basically, this is like a naive-based kind of situation. So there is a notion of prior, and then there is a notion of what you get from your data. So here, there is nothing you get from your data in terms of your information and classifying him. All information you have is prior.
Yeah.
By prior, I don't mean prior knowledge about the person. By data, I mean you have no prior knowledge about the person. What the prior means in today's situation is this number. It's my hard to. Let me share my screen. Awesome. Okay. Say this is my data set, and this is the last record, which is your customer you're talking about. We know nothing about his rows or columns. But you have a lot of other rows you know about in your data set, right? These are other customers. You know a lot about their different variables. In terms of, and then you also know what class that customer belongs, these other customers belong to. So maybe good customer, bad customer, good customer, bad customer, right? Whatever. But the last guy you obviously don't know. All you know is just his name. Say this is a name field. You only know his name. You know nothing about his behavior, economically, socially, education, whatever it is, relations with other people. So what the prior means is there's nothing you can predict about this guy's class. Sorry, this variable. This is the class variable, right? There's nothing. So you're trying to predict the probability of his class given the data. But the problem is you don't know anything about the data. You don't have the data. So all you can then do is you can only see what is the prior probability. What is the probability of any particular class happening in your data set in general. It means in general, say I don't know, Bank of America, whatever bank, say if 99, do you think 99% of any bank are fraudulent customers? I would think the other way around. Fraudsters or bad customers are usually a small minority. It may be 1%, maybe 20%. Right? So that is what prior information means. But in some other situation, the prior may say the other way around. So all you can say is in general, you can compute what is the probability of class 1, probability of C, which is class C equal to 1. You can compute what is probability of C equal to 0. And given no other information you have on data, all you can do is just use the prior information and say, hey, given just his name, and if I'm not using his name again in any, like racial or whatever thing, and I'm not trying to induce anything based on his name. All I know is nothing about. I have some random number about it, some ID, some token number that he got. All I can say is, okay, if I have no information by prior, in general, what we see is 89% of our customers are good. 11 customers are bad. They default. They don't pay their bills. They have a lot of issues. They do fraud, whatever it is.
Okay.
So that is all you can say about that.
But here I can say one more example, right?
Yep. Go ahead.
For instance, like example, Shashi applied a credit card, and I can classify Shashi as a brand new customer. I can classify Shashi as a bad customer. How means when you are filling your application, you are giving a lot of your demographical data, biography also. Okay, how many are Indians and how many are in this particular age and what is their work history? So based on these parameters, at least you can classify, looks like this guy is starting guy and such kind of people paid more college bills, school bills and everything. There is a risk like that. So we can classify that way also, right? Here in your example, you pointed only N, name, and you didn't take anything from above.
Yes, that's right.
Yeah, actually, that's what I've told him, like based upon his assets and financial income, we can predict whether he's going to accept or not. But he was not satisfied, means like the interview said it's not the right way.
I can see why he was not satisfied, because when he said he'd have no other information about it, he means it. Exactly what he means is very simple statement. He has no information about it, right? So what he gave is like a creative answer, but the thing is, you're answering for something that he did not give you as information. He said that does not exist, right? So from interview perspective, that's what I'm saying. He literally said, like what Venkat is mentioning or what you answered, you're using other variables about him. You're trying to say, okay, he paid this amount. All that is some variable in this data set, but your interviewer literally said no of these variables are available. He said this is not available. So no is a no, right? Yes is yes. It's like a one-word answer, one-word thing. So given that condition, how do you do? Then this is the only thing you can do.
Actually, the diplomatic answer, you're right. Maybe you would have placed the different way, like, okay, I have a similar behavioral customers, such kind of color, sex, age, demographic information based on the behavioral.
Then you are using these variables. That was not his puzzle, though. Yeah. But if you use that, in general, that is what will happen. If you have all these variables, some variables you have for these data is available. If you want to predict for this customer is good or bad, then you can obviously build an SVM, random forest, or whatever. You predict on this variable. You train on rest of it, and if it's a good model, if you tuned everything well, then it will predict automatically 0, 1. That's what the model is doing. Or you can do by paper as well, some rough calculation. These kind of customers I see, most of them seem to be good customers based on how his behavior is. Maybe he has a master's degree or PhD degree in in a field that has a lot of job market, maybe something like computer science, something like that, and we can see he doesn't have any kids, he's not married, he already has a car, he's paying his loans. If you have all that information, then you will say, okay, this kind of profile people in Bank of America seem to be doing very well, so I would classify him as a good customer. But then you're answering a separate question from what the interviewer asked, but in general situation, that's what you do. So what the interviewer asked is, you have none of this information, and all you can do is put this.
I might guess this. So I think every company, credit card company, have a number like 100. They can allow 100 fraudulent clients. If they have million clients, they can allow up to 100 clients as fraudulent. So if they did not reach that number yet, maybe they so far have only 50 clients who are fraudulent, but not 100. They can give him the credit card because they are still at 50, right? And they can allow up to 100.
Sure.
Maybe, I don't know, but maybe.
This is an innovative answer. It is out of the box is what I see.
Basically, you are taking risk. The risk level is not reached in the 100%, but they are still continue to take the risk.
Yeah, because they can take some risk. And they are ready to take some risk.
Yeah, but if the interviewer is experienced, what he would then say is, here's the idea of it. We can talk about this in a separate call. What is the interview process like in general? Like some of you already might know. There is a concept called peeling the onion. It's like a joke. Say you are an onion. You say something about the outermost layer. He will take that as if it is like a wrong thing, then he won't be satisfied at all. Or if he wants to give you a hint, he will give you some hints. But then there's something very out of the box. Then he will try to peel the onion because maybe he's testing you for generally how smart you are. Then it's a good answer. He doesn't have to peel the onion too much. But if he's testing you in machine learning or your statistics knowledge, right? If that is what his skill set is, then he has to peel the onion a little more. He can't say, okay, this is okay now, this is fine, right? He cannot close the game there. So what he would then say is go to the next layer of the onion. What he would say is, okay, say our bank does have a limit of 100 fraudulent customers, for example, that we can allow for. Say we are at 96 or whatever. Now, so based on your rule, you can say the next customer, you can allow him as whatever it is. But then what if he's a good customer and if you're thinking he's a fraudulent customer, then you're making a mistake, right? You're treating a good customer as if he's fraudulent. Another issue is, so these are ways of peeling onion. Then he can put in other things there very quickly on you and try to shake you up by saying, what about, how are you going to distinguish between a fraudulent customer who is going to cause a loss of $10 to the bank versus a fraudulent customer like, I don't know, like Harshad Mehta or somebody who is going to, put the bank down with like a $100 million loss to the bank,
Yeah.
What kind of a fraudulent customer, how would you evaluate it, right? So if I say, if your top 100 customers are like true gangsters or something, like real big hackers, you're basically shutting down the bank in a day,
Yeah.
On the thing. So he will start feeling it more and more. So it depends what he's testing you on, but he won't give you that. But it's a good answer to start with. So yeah, I'm not saying putting you down. I'm saying if you start with that, you should be ready for thinking more deep about it.
Yeah. Instead of not answering anything, at least answer something.
It depends what he's testing you on. So
sometimes they want to see like how is your thought process. See, they do not expect your exact answer.
Yeah. So in that case, you may be okay with those out-of-box answers. A good thing.
Yeah, but with just the name, nobody will give you the credit card, right, Pranit?
No one would do that. These days banks don't allow, but they have minimum requirement for them.
Yeah, minimum like income or.
Yeah, otherwise they will ask for some sort of a surety or a guarantor from another person, brother or something.
See, and not only that, right? For instance, like you are applying for insurance, right? You are not giving your information, but they may have your information from DMV or they may have your information from Sensex report, right? So there are certain, Census is giving, okay, what kind of people, what kind of geography, they are not collecting from you. I mean, even if you are filling an application only with the name, some basic parameters, but if your model is needing more parameters which you are not providing, and those parameters they can extract from their data as well as from government systems.
Sure, of course. The companies are smart. Always have a data warehouse can collect. All you do is you build your machine learning models. This is what the interviewer asked. Then all you can do is this. You cannot again assume they are going to give you data from somewhere. He's telling you there won't be data at all about it.
Yeah, like actually, I think he was expecting something from the machine learning perspective.
Yeah, so then you have to talk about higher probability.
But Pranit, here in Amazon, what is the fraud? Generally, you guys think like any terrorists are using the system, or if it's a bank, okay, anti-money laundering, right? In Amazon, you are giving services such as servers and software.
So Bitcoin, for example, you might have seen the Bitcoin rate is $15,000 or something today.
It's now 14,000 now.
Yeah, today it's in place. Yesterday it was 16.
Yeah. So I don't know how much you understand about the Bitcoin architecture, but that's a separate discussion. But some things I want to talk about it is the blockchain technology, the architecture is very computation intensive. What it does, it's like a ledger of keeping track of all Bitcoin users and how the trade is happening. So if I send money to Venkat, it will update not only in my record in Venkat's record, it will update on everybody's record in Bitcoin, all the millions of people. Every transaction needs to be updated on the entire graph structure again. Everyone has this latest information of who sent money to whom and who. Regardless of that person is someone that you know. So since it is computation intensive, someone has to share the burden of doing this processing. Because so many transactions are happening, you have to update this ledger with billions of records every single transaction. So this computational power, right now it is being shared in an open source way. So anyone who will provide his computer for free time for running the processing load in a distributed fashion is if you're allowing some of your power into the pool for distributed computing. Then all you need to do is download this Bitcoin mining software and then say, I will run this simple button or program. It will automatically help the whole Bitcoin technology run. So the thing is, a lot of people, this is called Bitcoin mining. You can do it legally. Because if I use only my laptop, I have limited power. I'm giving very little of my one drop required in the whole Bitcoin processing energy that is required, but I'm still contributing a little bit. So based on how much you contribute and how many transactions you literally help in finishing, you will be paid a small transaction fee by the blockchain architecture in terms of Bitcoin. So I will pay you 0.0001 Bitcoin. So that's a free way of gaining Bitcoin just by sharing your computational power. But the likelihood of gaining even that little Bitcoin is very, very low. So what fraudsters are doing is they want to run these programs on a very massive computational power. So if they can hack into AWS cloud resources and launch very large instances with so much computational power, right? You know, with like thousands of GPU computing style computational power. Then they are freely using AWS money and our servers and instances to run their Bitcoin mining software so that they can gain money with it. And if they end up getting, a quarter or a half Bitcoin, he has made, $14,000 or maybe $7,000 profit already. So we want to keep these guys away because Amazon is spending a lot of money in just data center maintenance, heating, cooling, employee payment, a lot of things. So we cannot waste this or OPEX, operational expenditure. So this is one kind of advanced part that happens. There are other things like simple customers like myself or someone who might intentionally not pay the bill. I will take a postpaid plan, I will use all instances and not pay a bill. I will vanish, I will not reply to his calls or emails. So that's another abuse of the system. Or I might have stolen somebody's credit card or... Oops.
Yes, sir. It's fresh brown.
Sorry, that's my Alexa. For some reason it turned on. Okay, so...
Sorry.
Alexa, shut down. Okay, so that also happened. Okay, so... things like that.
Alexa hacker our meeting.
Yeah, exactly. I don't know how it turned on. So I think somebody thought...
It heard something like some word which is interested or...
Yeah.
So you're talking about small customers.
Then you can also do credit card theft where you get a black market where you stole somebody's credit card before he blocks his credit card after it got stolen or lost it. You might have already used his credit card to launch an AWS instance to do other things. So compromises. Maybe you have a retail account. Maybe some neighbor has an Amazon retail account, but you somehow stole his information from his laptop. You will use the same credit card information to launch AWS account. That kind of compromises. Yeah. Cool. So yeah, I think let's call it a day here. Let's definitely do focus on finding a data set for sure. I might send in some assignment as well. Want to work on that.
Sure.
All right. Thank you. Have a good week. Good week. Bye.
Bye-bye.
Have a good one. Thanks. Bye.
Thank you. Bye.
Thank you. Bye.